All right.
Okie doke. Well, I'm no academic on switch mode power supplies, but I had a few years dealing with them. I started off with, believe it or not, vibrator power supplies. When I was young, it was about the late 1950s, and well, I was up in the country, and it's surprising me to me even today that the similarities between problems we have with vibrator power supplies and switch mode power supplies. So I remember now the AM broadcast signals weren't that good out west, and you'd have a farmer come here, and there was no electricity, and the only way of running a radio was 12 volts or 32 volt lighting fans. And they used to get very cranky when I'd fix their radios and stuff for them, and the noise from the vibrator power supply was sufficient enough to overcome the AM signals that were in the area, especially when they had a bet with their SP bookie. It got serious. Anyway, so tonight we're going to drag, I know you guys are all up the top end of the spectrum, so we're going to drag you down to the kilohertz region, even to DC. And the experiences and stuff I got from that. We'll start off, we'll discuss the very simple ones, which are the buck boost simple power supplies that are available on eBay, and of course in every transceiver these days there's some of those, and that's a copy of the the photograph of some of the ones that I use off eBay. There you get 10 for $10. Used to, I don't know what they are now, probably inflation's taken over, and you can buy them as buck ones or burst ones, and then we'll look at how they work. But you can put anything between 0 to 30 volts in there, and with that multi-turn pot, you can dial up what voltage you want on the outside. They are a little bit noisy. They're not too bad, but they are a little bit noisy. And if that's a problem, then you've just got to add extra filtering at the front end and the back end, and maybe shield them a bit. Okay, so let's proceed along and have a look. So all switch mode power supplies work on this state. That's the DC supply. So you start off, and we've shown here the transistor or the switching mode with just a switch. So as you switch it on, the voltage will rise up in there. The back EMF from that inductor there will go through and charge the output. And what we do is we monitor the volts that we dialed up with that multi-turn pot there. And when that volt reaches the desired voltage, it goes back and it turns that switch off. And when that switch off, the bottom state there, when it goes off, what happens then is that the back EMF from that inductor, we've stored this energy in that inductor, the back EMF goes around that circuit and maintains the battery via that switching diode. So that's all it's, basically the only thing you're doing is using the back EMF of the inductor and the stored energy that it's got to limit the current flow to start with, and then to try to reverse the back EMF is then directed back into the same energy. And of course, what they're doing is that as soon as the output load reaches the required voltage, the switch opens, and the stored energy in the inductor then goes back to the output and tries to maintain that voltage. When the voltage drops below our reference voltage that we've set, the switch will then close. So that's, they're all based on just that simple little operation. Now here's one here. What we've replaced that switch with a MOSFET, and it's driven by that circuit there. That's an NCP 3064, which is, there's hundreds of different chips around that will do exactly what we want, and similar to this one. So input there, this chip, there's an on-off signal in there. There's the inductor, and there's the load over there. And so what's happening, there's the feedback. What we're doing there, that's that multi-turn clock. We've just simplified with 2 resistors and a voltage divider. When that point's there, this chip has a reference voltage inside it. It compares that reference voltage to that voltage there, and that's what turns that MOSFET, that switch there, that's now inside. Inside that chip, the switch and stuff is inside the chip, so it's really self-contained. And if you have a look back at that original one I showed you, that's one of those sort of chips that was on that first slide. So that's the DC ones. They're pretty simple, and they really give any trouble. They've got current protection, so if you short the output, they just shut down. You've only got to remove the input voltage and then put it back on again, and they'll reset themselves, and everything's back to normal. So like the old vibrator supplies, shielding of them in RF wise is your critical point. And when they use them, and even though the newer radio, like the 7300 and the 705, all of those software-defined radios, and quite a lot of the ones preceding them, have oodles of these sort of supplies in the circuitry. And they're getting very, very good. The noise floor is quite low in them, and that's in the design. As I said, shielding's one thing, the input and output filters are another factor, and the black magic of them all on a transceiver is the board layout and where all the high current sections are in the printed circuit board, how you actually lay them out, and so that your high currents all are in a small amount of board that has overall resistance and stuff like that. And that's the key. So the black art that I call it in designing these properly is in that board layout and how well you do that. So that's all the low voltage ones. There's two there, the buck and the boost. They're not much difference. You can see there the stored energy when it's turned on through the MOSFET feeds into there, and then you turn it off and it feeds in there. The only difference between the buck one and the boost one is that one's just turning on and off, isn't it? Yeah. So when you're boosting, you bring that point up to the voltage, it turns off, and then in this case, the inductor adds to that voltage. So now the old voltage double circuits. And so the back EMF adds it, and you can then boost up to whatever level you want. And there's 10 voltage there, and the pulse that's turned on, turning on the MOSFET and stuff like that IC that we talked about before. And the amount they turn them on called pulse width modulation. So what they do, the more load you draw in, the longer they leave the half cycle on. And so if you don't got no load on it, this is very, very fine pulse. And then as the load builds up, the width of that pulse becomes longer and longer until, of course, you reach saturation point in there, which you've got to stop, and that's determined by the frequency you run the device. So this is the boost circuit. The inductor is actually up earlier in the circuitry. So what that one's showing is the transistor turned on and the charge going in, charging up, doing that. And then when it's turned off, the back EMF from that inductor there then adds to the original charge that's on the thing. And so the boost occurs and you can dial up then what voltage you want. Okay. Now we come to the bit that's getting serious. This is one where any voltage less than 50 volts is considered low voltage by the Standards Australia in AS 2000, I think it is. So what I was talking about previous to this is anything that's under 50 volts. From now on, we're talking about ones which are plugged into 240 and you've got high voltages. Prime thing here is your own safety. Now, it's good habits when you're servicing these things, good habits and knowledge of your environment. That's the key to it. Make a habit of both switching off the GPO and pulling the 3-pin plug before you touch it. Just make that a normal habit. And the beauty about this is you can quickly see that it's unplugged. Now, if when you turned it on before, it's had tsunami mass failure and it's gone kabang and the smoke comes, bits go everywhere. If that occurs, there's some chance of that switch in the GPO being welded shut. All right, you turn it off. Quite sometimes it'll actually show it's off. But touch it and you know that bloody well it's not. So that's why I developed that habit. When you're working on it, you can just quickly look there before you put your hands in and quickly look, it's unplugged, good, go ahead. Do that and Kev won't have to sign off a death certificate for you.
Well, but recently bought an isolation transformer doing that.
Yeah, but that's the isolation transformer is a good one to isolate it from the mains, but it's not going to stop the charge to that dump capacitor later on, which you'll see there. That's so make sure that, and we'll talk about that, some other issues later. But get in the habit of checking that all the time. And today in this lecture, I'd like to just look at a thing called fault metals. And it's important when you're looking at them, especially the bigger ones, the switch mode power supplies. And I'm talking ones now like these inverter welders, in 240 volt DC, 12 volt to 240 volt AC inverters and stuff like this. You've got to understand, what they are and develop these same techniques of working on them. Okay. Yeah, looking here, some various switch mode power supplies in my workshop. The first one is the inverter welder. Now that one, there's an interesting thing about when I bought that on eBay, and they said it's capable of 220 amps, and it's got a 10 amp plug on it. I said, well, these buggers must have found something new because that doesn't add up. And when it come, sure enough, they had the 10 amp supply on it. And when I wound it up to full scale, it produced 140 amps, which is what you expect. So I thought, these Chinese people are coming. So I pulled it apart, and in there's a multi-turn pot. And so I thought, and it looked as if it was on the current sensing of the output, which most welders have accepted. They dial up the current, the voltage, it stays the same. So I turned it one way, and oops, it's now 150 amps. I said, I'll keep going. Sure enough, 220 amps, 50 volts come out of that supply. And what they've done is just turn back the current right off so that when the certifiers looked at it, oh yes, that current doesn't pull any more than 10 amps. Mine's still got the 10 amp plug on it, but it's now producing 200 and something amps. So that's story. That's about 5 kVA, 6 kVA. That one. That one on the side there is a typical one you buy off eBay. They're not bad. Sometimes they're a little bit noisy, and it's just purely filtering and the shielding and stuff, the way they do the shielding. And one thing I learned when I was working on vibrator power supplies, that when the farmer used to go crook and say, can't hear it. What we used to do is we used to open it up and we'd move, all the earthing came back to this one bar in them, I remember. And what we used to do is put, make a connection between that earth bar and the shielding case. And we would move it around and there'd be one spot where the noise got right away. And of course, that's where you soldered it in, gave it back to the farmer, and you could hear his bloody races again. All's well. And so that's why I'm saying that's the same effect as what we're talking about when they were designing them, is how important that guy that did the design laid out the circuit, stuff like that. And I think that's a critical piece of, plus of course you can't avoid all the filtering. That one there is the thing I call a wallwart. And wallwarts are just those plug-in power supplies that, you know, they're a dime a dozen, everything runs on them these days. They're quite often start off quite good, and then after a number of years they start going very noisy and stuff like that. And you'll generally find that the capacitors are starting to get lose their capacitance, and oh, who knows what else, but they become noisy quite out of the blue. The other one is one that just come into me. As you can see, it's black. And the reason it's black there is it exploded. And that's a LED floodlight, LED floodlight. And it's got a 240 volt to 30 volt output, and it's limited to, I think, in this case, it's a 30 watt LED in the front of it. And it's a current limited switch mode power supply. So that's just an assortment I've got. We actually managed to repair that one. Lord knows why, because when I finally looked up, I can actually buy the switch mode power supply as a spare part, but I could buy a whole LED 30 watt cheaper. So yeah, that's why, you know, the repair of small ones now is just generally uneconomic. And that, of course, is very true of all the wallwart ones. You can buy them cheaper than you can buy half the components. So that's why that now most of the repair work and stuff is only for the bigger. The only viable repair work is on the bigger units. That's a close-up view of it. You can see that back end of that one where it's all sealed up in that box, but the sealing compound was, and that one was quite soft, and you can dig it out with a sharp screwdriver and stuff. And what woke me up to that was that there was quite a bit of it missing, and there was that's the back end of it, and the bridge diode and stuff like that, it all just exploded. Okay, so looking at test equipment now. First, the Crow. That's one that was actually developed by Tektronix, and it was specifically for people maintaining and servicing switch mode power supplies. Now, it's a 2-channel Crow, but both channels are differential input, as they appear there. You can have the 2 earths on those Crows, you can have them 600 volts apart, and you can still look at the high level. And when you're looking at things you've got to look at, then remember before I said we're talking about the switch on time and the switch off time. And there's another important fact is the dead time. So when one cycle, when it's flat out and it's producing as max power it can, the on time is virtually the full cycle of the frequency it's running at. And same on the bottom side. So what you've got to have between switching from one transistor to the other, you've got to have a dead time in the middle. If you don't, the Vesuvius occurs again. And we'll tell you how we solve that problem. The next thing, that's just a straight mega. It's a 500-volt mega, and AS2000 says that after you repair the unit, you've got to check its insulation resistance is greater than 100 megohms, and the earth read is less than 1 ohm. That's my secret weapon. It comes back from the early days of electricity, and they used to use test lamps. But it does the same thing, and we'll talk about that thing later. Its sole job is limiting fault current, and that is a tong. I use that as probably just as a multimeter, but it's a clip-on device, and it measures DC and AC current. And believe it or not, it cost me less than $50 because my previous one died, and for $50, I figure it's not worth trying to find out what's wrong with it. So looking at, we talked about that Crow, the big advantage, it's 100 meg Crow, and it'll, and the big advantage, of course, is that those two channels can be, you can see the high side voltage and the low side voltage at the same time. And you can see signals which are only 1 volt peak to peak, you know, so on the top of those ones. Okay, the name we talked about that before, can you get 500 volts, and the movement scale is more than 3 ohms. And that's we've got to use that as your last test. And we talked about that one. That's the closer view of the motor. And they're quite, as I said, $50 on eBay, and they're really handy. In fact, when I'm out using the field, that's the only motor I take nowadays. It's so versatile. Now, talk about this thing. This is the fault current limiter. What you see there is 2 bulbs, and those 2 bulbs, I can rearrange those banana plugs at the top so that the 2 bulbs can be in series, or we can just have one of them, or we can put the 2 in parallel. And the reason for that is that as you go up the size of the supply, you'll need to be able to put the lights in parallel. If you're working on one of those little wall warts or something like that, you put the 2 in series. Now, what happens with them is that when you first turn a switch mode power supply, you can see there's a plug, 3-pin plug on one end, 3-pin socket on the other. Now, a lot of the suppliers you work with have already got a 3-pin plug on them. If I get ones in that are hardwired, I put a plug on them and plug them into that. So as you turn it on, and you'll see later, the first thing that happens is it goes through the bridge rectifier and charges up this capacitor. So once that's doing that, the lights will light up. If they stay on, you know immediately you've got a problem, and you still haven't blown the fuse. So all I'm doing there is putting resistance in series with my with the appliance I'm testing, so that if something goes wrong, it doesn't explode in front of it. And maybe hundreds of dollars, I see. Let's talk about fault current a little bit. Oh, sorry. There's the circuit of that thing. It's not easy to see. Yeah, there's the 3-pin plug, and there's my banana plugs, the 2 lamps in the middle, and that, and the neutral is plugged right through. Now, remember, on a 3-pin plug is a standard. They set up a standard with the face that looks at you. Top left is active, top right's neutral, and the bottom one, of course, is Earth. So that's wired up. So the active line is the one that the lights are in series with. Okay. Now let's talk about power system, fault systems, and this is just giving you a bit of an insight into the problems we have in the electrical transmission systems and generating systems and stuff about fault levels. Now remember, last year, was it last year? I think it was, we had a big failure, and we'll talk about that one. Now at your local power station, each set is capable of 450 megawatts. That's each set in the power station. And there could be 10 of them in the couple of power stations that we've got. So the 750 watts is equal to 1 horsepower. So the actual shaft on that generator is 1 over 750. In other words, you're dividing by 750 times the 450 megawatts. 5,000 to bring the megawatts to kilowatts, 5,000 to bring it back to watts. So you end up with 600,000 horsepower on the shaft, driving that thing. Now, you wouldn't stand in front of your car that develops 200 horsepower. You know, when something goes wrong with these things, it's serious business. Let's have a look. Okay. Have I seen failure that happened 12 months ago or something like that? Put the lights out over most of the states. Let's have a look around here. See these holes in the roof? That's where bits of cast iron have gone through the roof. There was a 300 kg block of cast iron embedded in the roof of that place that they had to remove before they could go and do any investigation. Now, I happen to know one of the young lads who used to work with us. He was on shift at the time this happened. And he was actually looking at the output from Caloid, and he seen this set. It was generating about 450 megawatts or thereabouts. And he said, oh, that looks pretty normal. And next minute he looked at, you couldn't believe it. Instead of 450 megawatts going out, there was 50 megawatts coming back in. And he said, you couldn't believe it. He said, this is not right. It's gone wrong with the instrumentation. And next minute he was fronted with about God knows how many thousand alarms coming up. And he says, maybe that was right. Now, the investigation of this is not yet finished because of the COVID things and the restrictions they've had. But what happened that we can understand so far is that there was some guy who was working on the battery supply to this particular alternator. And that is the thing that supplies all the protection circuits and stuff that are associated around that. What happened was that the reason why he's seen 450 megawatts out, that was perfectly normal. But the 50 megawatts coming in, what happened was that something failed there and it started tripping things, putting things out of action. What happened was that the excitation to that alternator dropped off. The steam valve was supplying steam to the turbine here had shut off, which is the first thing you think to do. You've got to shut the steam down pretty quickly. And there's normally a circuit breaker on the back of that alternator between that and the system bus. That didn't open. No one knows why it didn't open, but we presume because the tripping supply to that was, and it's all an assumption, so the tripping supply to that had failed, and that set off, that fortunately shut the steam down. But we also think it shut off the oil pump to one of the bearings. Oh. Now, if you have a look there, have a look at that device.
What is that?
That's a lump of shaft. Now, the shaft is about that round, right? And you can
Find that out of the front there.
Now, my suspicion, and I'm only observing from a distance, my suspicion is that it came from there.
Yeah, that's what, yeah, from in there.
Yeah,
Yeah.
and that's the bearing that failed.
Yeah.
All right. Now that, as I said, that shaft is about that big,
Hmm.
and you can see the height of it. There's those, where are we?
You wouldn't want to be in there when they went on.
Oh, God, no, they were just so lucky that there was no one on the turbine floor at the time.
So that just sheared off that, right?
Sheared off that thing. Now, it's either come from there, which is like, there's nothing
Yeah.
there, there should be something in there.
Because that's the steam turbine, obviously.
Yeah.
And then that's the
the
shaft.
steam- That's the
Right?
steam turbine.
Yeah,
And right back here is where the low pressure fans are. And the low pressure fans are quite huge. They're about 12 foot in diameter, and they've got blades on them like this that are quite solid. So when that bearing failed, of course, everything went in. Big blades of the turbine are the things that have gone through the roof.
oh,
Right. And you can see quite a lot of damage around, which is the back end of that turbine where the low pressure end is. So you can see from that you don't muck around with these things.
so actually you can put it into perspective of the size, is look at the handrails on the steps.
Yeah. Yeah. So that's a big chunk of steel, and it's obviously gone up in the air somewhere. And man, you can see it's actually buried itself in the turbine floor.
Mm.
Anyway,
The whole bearing cage disappeared.
yes, yeah, and I once again, I don't know, but that big 300 kg block of cast iron that was buried in the roof was probably the top of that bearing.
Mm.
As it departed. Anyway,
So what you're saying, there's a lot of energy available at your power plant.
a lot of energy. Yes, and that's what we're talking about, fault levels. Okay. The service, now it's a lot better. Fault levels in your own home, a lot more manageable than that. Thank God. The service fuse on your house, the service fuse out on the pole is normally 80 amps or so. And it's what they call a HRC fuse. It's a high rupturing capacity fuse. It's quite a large one sometimes. It used to be about that big, but now they've got them down to about the size. Because the next fuse in line, down that line, is a 20 amp circuit breaker. Now, circuit breakers too have got a lot more ratings than that 20 amps. The circuit breakers that you use in most houses these days are capable of interrupting 4,500 amps as they are. Now, what I mean, they've got to open and disconnect the supply. If you open it and the arc continues across them, they haven't opened up. So they've got to be capable of opening 4,500 amps at 240 volts. All right. The other rating on them is the type of curve that they operate on. And the curve normally is a type C operating curve. And that means, to find it very simply, that circuit breaker, if you've got, say, 25 amps on it, will probably trip in about, it could be okay, quite a few seconds to trip. Could be 25, 30 seconds or something. If you put 4,500 amps through it, it trips in less than 1 cycle. And so it's an exponential curve. So like the current is up here and the time is up here. So it's a long time for it to trip with just 25 amps on, but it's very, very quick at fault current levels. And most of our protection systems in the transmission system are of that type. So that's why I use this device. It protects you against the
Point.
under volcanic eruptions.
Mm.
Yeah. Okay, let's now look at the block diagram of a high voltage input switchbase supply. You come in at the end, at the beginning, come in here, the first thing you generally strike, other than some filtering, there's generally filtering in front of that, is a bridge rectifier. Now, of course, if that bridge fails, you've got a short circuit right across that thing. And if you've got nothing limiting the fault current, you're going to get up with 4,500 amps. Probably not in your home, but that's a possibility. That's what you're going to design for. The next thing on the, just keep using, next thing on the line, they told me it's a filter, and the dump capacitor, which is generally, 200, 300 microfarads, and the voltage there is going to be in just 400 volts or just under. So you've got a lot of energy in that capacitor. So if it goes faulty, it's going to go bang, and it's going to be fed by that AC mains going in. So there's another eruption point. The next thing in line is in this case, a MOSFET, which is doing that switching. It's switching the current through that next transformer. It's switching it on and off at probably about 200 kilohertz, or just under generally. And it's a ratio transformer, brings it down to the low voltage of whatever you've got. And so sometimes they've got multiple windings on that, but simply there's just another bridge rectifier and some more filtering on the output in that area there. What we can see here is that they have some feedback through an opto isolator, and that's that voltage switching that we were talking about before with those simple switch mode supplies. And you've got to have, when you're designing the board for these switch mode power supplies, you've got to have isolation between the low voltage side and the high voltage side. That's mandatory. And it's got to be capable of isolating, it's got to be capable of at least 500 volts, probably 1,000 volts if you do it properly. So if you have a look at the circuit boards, they've generally got the middle of the circuit board milled out. There's a gap in there. And that's to help achieve this high voltage, low voltage isolation. So that opto isolator feeds back into that pulse width modulation system that we're doing, where it actually changes the width of the pulse depending on the load demand, and switches on and off compared to as per by the voltage. There's generally two lots of control on that pulse width modulator. There's, there we are. You can see one coming out of here. Generally speaking, that's a little current transformer. It's quite often quite small, that gate round, and it's got a few hundred turns on it. And it's actually it's probably a 5 amps to 10 amps to a few milliamps or something like that. And they feed the output of that current transformer, which is the current that's passing through that MOSFET, which is supplying all the energy to it, and they bring that back here, and that's there's another pot in there, and it's compared to a reference voltage, so that's what makes them shut down when you're exceeding the load. So when you're repairing them, what you've got to look for is if something's gone wrong there, what's shutting that thing down. Quite often you turn it on, there's nothing, no damage, nothing, and what you find is that there's no pulse width modulation. Not that transistor, that MOSFET there is not being switched on and off. So you've got to find, okay, now why is that case? Is it the current side of the circuit that's stopping it, or is it the voltage side of the circuit that's stopping it? So that's critical. So that's generally a quick, simple sort of block diagram. Here's another one of it. It's got a few things. That one there shows that isolation I was talking about before. That's the isolation band. So this side of the circuit has got to be physically as well as electrically isolated from that part of the circuit. There's a current reference and there's a current coming back from that MOSFETs into there, and here's the voltage circuit. Back in there, that's the voltage side. So AC power in there, rectified, 400 volts DC with that dump capacitor and the MOSFETs in there, switching that transformer backwards and forwards at 200 kilohertz. And then on the other side, high frequency rectifiers. Remember the diodes here, they're running at upwards to 200 kilohertz. So if you use, say, a diode like a 1N4004, then the capacitance of that diode is too high or to work at these frequencies, especially when you start trying to draw power.
So where's the control circuit getting its DC from to be a control circuit?
Sometimes they've got a little control circuit which feeds off the inputs as a separate rectifier from the mains. Other times it's actually fed from another winding on that transformer. So there's two different modes there of doing. We'll go and have a look at some of the circuits. Yeah, well, that's the thing. Why don't we put that one in? Oh, yeah, there's that little part. Where are we? There. You can see there, that's a sign of the pulse width modulation. You can see that the transistor is switched on when there's a big load and switched on for just about the whole half cycle. And when the load's light, it's more like, well, that one there, you see it's only switched on for a short period of time. And of course, that's why I use those crows. Look at that, I can tell as I load the load up, I should see the on time for those particular transistors increase and decrease as I change the load. I just don't care. Another piece of gear that I've got a whole roll, it'll be rolled, yeah, I suppose about 20, 30 meters of stainless steel wire. And what I do when I'm checking these, the bigger power supplies, I've got a couple of big top welding cables, and my workshop's got a big car entry door on one side and the entry side. So I take these two leads out, put one out through the entry door, another one out through the garage door, and I unroll this big lump of stainless steel wire out on the lawn, much to my wife's disgust. And so to adjust the current on there, I just move that welding clamp along this wire until it comes up to whatever load I'm trying to get. So sometimes you're going over 100 amps, 200 amps or something like that. So yeah, another hand, a simple sort of piece of test gear, costs you nothing. You get a stage, you can just use all the fencing wire if you want to do no different. Okay, now here's the circuit. Now we get into the touchy bits. 240 volts coming in there. First thing we strike is F6A, the fuse. Now that fuse is quite important. It's got to be able to interrupt the fault current. If we get a failure in that bridge rectifier and stuff like that, where it just goes short circuit, then that fuse has got to interrupt the 240 volt supply. Now, quite often that's just a glass fuse. But what you're going to make sure is these days is that that fuse is rated at 240 volts. Because there's a lot of glass fuses that are just designed for low voltage like work. So just check on that. Whatever it's current is marked, you just look on the side, you can see what amps it is, if there's anything left of it. Some of those fuses are ceramic ones these days, and they're generally filled with sand. Even some of the glass ones are filled with sand. And the idea of the sands is that it heats up quickly, blows the fuse, and it melts some of the sand into glass and helps extinguish the arc.
Those are usually soldering ones, aren't they?
Yes, sometimes they're soldering ones, other times they're clipping ones. Yeah, you get a big variety of them. So that's the next thing there is the filter. That's the RF filter going in to stopping any of the noise that's generated up in the air. You know, that's especially a 5 kilowatt CWA output stage, isn't it? If it's in there, so there's quite the prosperity, a lot of noise coming back up the mains, and that's quite often an issue of noise. So we then, that's the filter, there's a capacitors on that side of the filter capacity, that's all that bit is the RF filter. We then go into the bridge rectifier, and out of between there and there is just under 400 volts, generally speaking. Now, in there, that device there's a negative temperature resistor. And the idea of that is that when you first switch it on, if you happen to switch on and close the switch at the peak of the 50 hertz cycle, then the inrush current charging those capacitors is quite high. And of course, what that does, it hits that resistor up and reduces that until those capacitors charge up. And that then, once they charge up and stuff like this, you can then start a control circuit and start switching it. So, of course, once those dump capacitors there charge up, there's two in series there. That's one of the very early type of switch mode supplies that was designed for 240 or 110 volt operation as a separate ones. Don't see many of them these days. They're quite capable of running from about 80 volts up to 250. The next point that you've got to look at is those two resistors there. They're the bleed resistors. Now, like in the old days of radio, they're a high value resistor. They're, in that case, 150 k ohms. Anything getting up around the 1 meg mark and stuff like that has the possibility of going high. In fact, they've got the possibility of open circuit. So if they're not there, those capacitors, when you turn them off, or the fuse blowers and stuff, if those resistors aren't intact, then for days you've got 200 or 300 volts on that capacitor, and they hit. So that's from experience. Okay, so there's, you're talking about 360, and that's for, it's a bit low there, but generally it's up just under 400 volts. In this circuit, we've got bipolar transistors. And that was common in the early computer power supplies and stuff like that. But they did quite well. The thing that I forgot to mention when I did the talk at Red Creek is those dump capacitors there have got to be a low ESR capacitor. In other words, they've got to have low series resistance. Now, in the early days, that was the main source of failure. In the late 1970s, early 1980s, when we started building these things to power our computers in the substations, the biggest failure rate was these capacitors because they were just standard electrolytic capacitors. And they'd last about 2 or 3 months, and then they just go pop. And I know we really had no answers for it, so we developed a technique where you could actually change them live online and increase our uptimes.
You're standing on a rubber mat.
Yeah, and we used to take the earth off the scope soldering lines and stuff like that, you know. Yeah, but so ESR, nowadays, of course, you can get ESR capacitors, low ESR capacitors quite readily, and that problem very rarely ever occurs these days. Okay, so this particular one is using bipolar transistors. here is that controller chip with all the inside workers. There's an isolator. There's some logic there that there's the current voltage comparators there. It develops a reference voltage in it that's used both for the voltage and the current. Is internal, and then there's some logic there to give us the dead times and stuff that we talked about before, and then the output, two outputs there, and a little bit of amplification there, or drive it, just impedance that because it just increases the drive. That's the driver transformer, which sometimes you don't see these days because they've changed the design fashion as they go along, but they're used to be all the early computer power supplies that way. And that drives those two transistors, which put that, the 400 volts across that main winding there, and it puts it on and takes it off. And same thing, we use the back EMF of that to drive it. And that's where the dead time circuitry is quite important that you're getting that, because if those two transistors both turn on at the same time, you've got 400 volts there, down through that one to where say you've got a dead short. Now, not only have you got the fault current that's available through the bridge rectifier that's added to by the dumper from those capacitors, so all that energy just goes kabang, and that's why they erupt. Okay, so and then looking further over here, the output transformers, and there's one here. There's that's the winding and rectifiers there that supply the power to that chip.
So what gets it started?
The initial inrush, when they design them, one of those transistors will actually have a slightly different gain to the other. So one will turn on at the start. Once it starts to turn on, that transformer there turns one hard on and the other one hard off, just by the phasing of it. Yeah, so you get this big pulse as you turn it on. And that then there's enough voltage to click this circuitry off. That's the actual main output winding. It's a 24 volt output. You see the rectifiers there. Now those rectifiers have got to be a low capacitance rectifier stuff as well. And we come up with now in this case they didn't use the CT that's in the other side of things. This is a different variation. They put a little bit of that's 3.9 milliamps in there. It's such a shunt, and they measure the voltage across that shunt, and that comes back, and that's the current limiting circuit. Also coming back through there is the voltage circuit as well. So that's a 24 volt, 10 amp, I think, something supply from there.
All this has to be real time at 200 kilohertz.
Yes. Yeah. Okay, let's have another look at. There's one more modern one. There, 240 volt going in. There's the fuse. That's just a switch on off switch. There's the thermal resistor in there. The RF choke up through the bridge diode, and in this particular case, the MOSFETs are inside that chip. Now, because MOSFETs, they were the next advance in switch motor power supplies. When we moved from those bipolar transistors to MOSFETs, because they've got 0 volts across the source drain, there's a big increase in efficiency. We had less heat generated by the supply, so the reliability and the efficiency came up when we went from bipolar transistors to MOSFETs. It's going to come up again because now things like IGBTs are becoming available, and they're capable of running at these sort of frequencies, and they're capable of handling a lot more power. And so they're the latest innovation.
Don't really make any switching BJTs.
Don't they?
I remember reading that it's not, because everyone just uses pads for their power.
Yeah, I did. I
Just can't really hide them.
well, like that's the supply chain rather than a technical thing, isn't it?
That's not making BJTs other than switch.
Well, it's interesting. I was talking to a chap the other day who he's into renewable energies and stuff like this, and he makes other version of these things. And what this device does, it corrects the power factor on the power system, and it's series parallel capacitance thing like this. It can act as an inductor, or it can act as a capacitor. And all they do is they generate a 415 or 240, whatever you want to talk about, and they actually inject into this system a current or a voltage that generates, and it will generate with a leading power factor. In other words, it's a leading current, and it corrects the power factor of the system. Now, to power authorities, this is important because we don't get paid for reactive energy. And you've got to have bigger wires and stuff like this, that's a big expense. He generates one, he's got built one of these that runs at 17 kVA, and it runs on EFETs, and he reckons that was the biggest breakthrough that he had. That welder I got has got EFETs in it. So yeah, I don't know. I'm a retired guy, so I'm not keeping up with things as much as I used to. But yeah, that's a computer power supply. You can see all the different voltages out there, and they're all done with just windings. Now, what they do in these cases is they just regulate one winding, and all the others just fall in the line from that.
Well, coming back to my earlier question, I noticed that the controller gets its DC from the R7.
Yes, yeah, yep, and that's another common practice too. Yeah. Okie doke. Another interesting little thing is there that little device down here, which is just a voltage detector, and it actually fires a control voltage through that circuit here. So what I'm really saying with these, that it doesn't matter. I very rarely do I get ones that I've got to repair that I can get a circuit from, but they all fall into the same sort of thing. So you just got to go through them and trace out the circuit. I use quite often when I'm doing it. One of my practices is I've got all various coloured permanent marker pens, and I use my multimeter on the ohm scale that's got the beeper on it, and I can trace the circuit through, and I colour on the backside of the printed circuit board what they are. You know, I use blue and brown for the AC coming in, which is active and which is negative, and then I use red and black once it becomes DC, and I'll use other colours to think of. I've got lumps of paper with down and what I've actually used what colour for, and it helps you get a picture in your mind of how that circuit board's laid out. And you just, it's the old belling outside of things, just with a meter on it, where it beeps on a short circuit. And you just got to make sure, and I vary that sometimes. Sometimes I use the diode protection side of that meter, where I want to make sure that if there's a diode in series with it, it'll still beep. And other times when I use the thing, it generally doesn't beep across the diode, the forward diode, when you put it across that. So that's another handy little trick that you can use. Okie doke. Well, that's about it. This reflection from that last lecture, I did some afterthoughts of that one. There's a good tutorial on switch mode power supplies and pulse width modulation on that site. It's I thought it was well laid out and well experienced, so that gets you wide around what it is. Secondly, I talked about this time the ESR feature electric capacitors. It's important that the effective resistance across those things is between 0.01 and 0.1 of an ohm. In other words, they can handle rough current. And next, I think it was Peter Schrader that asked, what's the highest failure rate? I was a smart ass, and I said the fuse. Well, in most cases, something happens, the fuse blows at least, but there might be some other reason for it. But as I said, once we got the low ESR capacitors, we improved it. Once we got rid of bipolar transistors, it improved again. The MOSFETs and the efficiency. You're looking at efficiencies around about the low 90s, mid 90% efficiency for motion switch motors these days. So that's a big thing. So that's about it.
Apart from the EMC.
I really just started, mate.
Well, that EMC is a major thing these days, and especially with solar systems. We all know about them, the inverter noises and stuff like this. There's a big article on ones that were approved in Australia, and there's a whole lot of legal action in the United States because they got approval over there, and they were making much bigger claims than they were actually getting. So another job for you.
Can we bring the Zoomers back up on the screen, see if there's any questions? Or anybody got any questions for Bob at all, or anything you want to do ask or fill in?
What's the switch back there supply?
Maybe
Bob, I might just make a little comment. Is anyone occasionally watching the YouTube video channel called Third Signal Path?
I see it.
Yeah, really, really good. When he's preparing test equipment, he aims for that switch out power supply. The numbers of times he's come up with fixing up these.
Yeah.
So the signal path is really, really good.
Well, Mark, that's a favourite channel.
Yeah.
Yeah, I think, and that wizardry of being able to lay out those boards, it just never ceases to amaze me how good some guys are. You guys can use it time and time again. The first time you get them under an EMC test, but they're pretty good. And you might improve on them. Other guys that design them, it's a battle. I know at one stage we used to buy those capacitors. They were 0.1, 0.01 or something like that, 3,000 volt, little blue ones. And we used to buy them by the bucket load. It was just a matter of trying to find in the circuit where the noise was emitting from. And took one of these across it and it just soaked up a bit.
Any questions?
Any questions from any of you Zoomers out there? Andrew, John, Peter, Frank?
I have a question, Bob. Once the schematics you showed a fuse on the neutral coming in, not on the line.
Yeah, that's right.
Right.
Yeah, you always using the other side of it. But that's what I said. There is a standard that you should make a 3-pin plug. And generally these days they're covered. So you can't get it wrong. But if you look at the GPO that comes out the wall, that top left one should be active. Mind you, if you're an old house that was done around in the late 1940s and early 50s, that's not necessarily the case.
What about just connecting DC up to some of these things with a set of screw terminal? You should get the labeling right, but the uninitiated get it wrong.
Yeah. Yes, there's a wide range, isn't there, of quality for the switchmate flies and stuff. And generally the cheaper ones come out, and some of them I've come across just have none of that RF filtering on the input side at all.
I noticed that JCAR, they usually go for some lower quality things, but they've got quite a lot of minimal ones in their catalogue.
Yeah, it doesn't seem, I've seen a few cases where I don't think I've ever seen any of the really expensive ones that are lacking it, but I've seen ones that are cheap, quite good. And next time, you go to another one that's lousy.
Well, thanks, Bob.
Yeah,
On behalf of everybody, those of us who are here and on the Zoom, thank you very much for a very insightful talk again. I've learned something yet again in seeing this, and thanks very much for giving us that talk.
Nice welcome. I think I've just about got your computer under control.
Oh, you got it. Andrea, I think we can drop the Zoom off now. There's just a few little bit of business stuff to go through and chat.
So just Kevin, one comment from me, Peter, VK3A.
Go ahead.
Go ahead, Peter.
Just if you are shopping for power supplies, I'd recommend the Meanwell or the Power Monic, I think. Power supplies, spend a bit of extra money. They'll last a lot longer and a bit cleaner, and they run a lot cooler.
Yes, I agree with that, Peter. Yeah. I don't think I've repaired that many Meanwell ones, and the ones that I do get to repair, it's been lightning damage or something like that.
Yeah.
All right, guys, if there's nothing more, I will end the meeting at that point. Thanks for joining.
That's all right. I'll keep going and fixing Ivanhoe. See ya.
Actually could get a job in Borneo.
All right. Have a good night, everyone.
Good night all.